All right, well, hey everybody. This is the first part of the torque part two. For it's a long story, but when I originally recorded this, uh, I had the mic turned off for this part, so I'm gonna go back and re-record it now. Um, so if you notice me wearing a slightly different dress shirt underneath my sweater, that's why. Um, but in the previous lecture, which was a while ago, which was before spring break and all this craziness, we talked about how energy conservation can be used to figure out how fast objects roll down inclines. Because not only is there what I would call the center of mass kinetic energy, there's also rotational kinetic energy. And the gravitational potential energy is converted into both of those kinetic energies as it rolls down the thing, which means that the speed at which the thing rolls depends on what rotational inertia that object has. So if you remember the race that we had between the hollow wheel and the wooden solid wheel, both of which were almost exactly the same mass when you put it on a scale. Do you remember which one won? So if you go back and you watch it, the wooden wheel wins each time. And the reason it wins is because the wooden wheel has lower rotational inertia than the hollow wheel, because the hollow wheel has all that mass at as far away as it can from the center of the axis of rotation, whereas the wooden wheel is solid, and so some of the mass is really close to the axis of rotation, and only part of it is at the very edge. And so it is less difficult to spin up that wooden wheel than it would be the sort of hollow hoop. And so as a result, it can zip down the ramp faster. So that's what we learned last time. And by the way, rotational inertia is often referred to as moment of inertia. Maybe if you took physics in high school, you had heard it referred to as moment of inertia. These are two different names for the same thing. But I like calling it rotational inertia because it's a little bit less jargony. Anyway, so here we go. Rotational kinetic energy is this formula. So I is the rotational inertia. Omega is the angular speed, right? So there's something that's spinning around here. Let's see if I can. I can't. Here we go. It's towards me and then again. Okay, I'm still getting used to this green screen. There we go. So this is the rotational kinetic energy which we used last time, and different objects have different values for I. Both my dogs are here watching. They're really cute. So often we're going to use this equation, and when we use this equation, the following equation is very helpful, which I introduced way back before midterm 1, which is that the velocity of the edge of this wheel is related to the radius times the angular speed, which means the angular speed is related to the velocity divided by the radius, like that. And so often we want to figure out the rotational kinetic energy. When we get here, the next step is often there. So for example, if you are driving your car and you want to know what's the rotational kinetic energy of just your wheels, just the fact that they're rotating, not necessarily moving forward, but just rotating, well then you take the speed of your car, divide by the radius of your wheels, and that would give you the angular speed. Stick that into there, try to figure out what the rotational inertia of your wheels are. Anyway, this is often very, very helpful with this. Heads up. Now today I'm going to calculate the rotational inertia just for one situation. I don't expect you to be able to do this on midterms or things like that, but I need you to see it once just to know where it's coming from. And this is what they do in the Columbus campus anyway, so I'm trying to stay consistent here. But this is the scary-looking formula. And so what's going to happen is we're going to take some object that's rotating, and we're going to break it up into tiny little pieces. Each piece has a tiny amount of mass, m sub I. Each piece has some distance to the axis of rotation there, right? So if we're rotating about some axis there, there's some axis of rotation here, and so what is, this distance or that distance? So if you do that, for enough things, that will give you what the rotational inertia is. So I'll break this down in a couple steps for you. Now, I showed you this table before. This is the table from the book. You will have this table on midterm 2 to look at. And as I may have said before, it's interesting to note the similarities between these two things. So for example, if you take these radii, R1 and R2, and set them equal to each other, then you basically get twice R1 here. And so a half times twice R1 gives you mr squared, which is this. So there's like these connections between these two things. And then this one down here, which is like that wooden wheel that we rolled down the ramp. This one, if you take this and you set R1 equal to 0, that gives you 1/2 mr2 squared, which is basically the same thing as this. So it's good to be able to see the connections between these two things. The next slide, this is the table continued, and this is a rod that's rotating about its center. But interestingly, if you try to rotate the rod about the end, then the rotational inertia is actually larger. It's 1/3 ml squared instead of 1/12, which kind of makes sense because you have more stuff that's further away from the axis of rotation, right? So this is L away from the axis of rotation, whereas this is L/2 away from the axis of rotation at most, right? So it makes a little bit of sense that this is a little harder to spin up and spin down. And then we have the equations for spheres. So there could be a question on astronomy about things spinning. A lot of stuff in astronomy is the solid sphere, not the thin. So the sun is not hollow inside. Just trust me on that one. There's ways that we can figure it out without actually going there. But so these equations are there too. In the next few slides, we're going to consider these two. Yeah, I don't expect you to memorize these. I don't expect you to derive these. I'm going to show you how to derive this one real quick. I'm sorry, this one. We're going to show you how to derive this one real quick. And I'll show you where that comes from. All right, here we go. So rotating this thing about at the end, and we're going to break it up into the tiny little chunks, right? So the mass of each chunk, if it's a total mass of m, the mass of each little tiny chunk would be m divided by n, right? So there you go. So let's say we break it up into 3 little pieces like these ants that are sort of holding each other. Here n would be equal to 3. So the mass of each ant would be m divided by 3, right? N is 3 in this case. And so we can stick that back in here, like that. Now you notice that n does not depend on which ant we're talking about, right? It doesn't matter whether it's ant number 1, 2, or 3. It's 3 ants that we're dealing with here. And so we can bring these out of the sum as a constant. The total mass does not depend on which ant we're talking about, so that can come out as a constant. And so we've taken this scary looking thing and made it into a slightly less scary looking thing, because now we just got to deal with this thing. So to deal with that, we need some formula for the distance from each ant to the axis of rotation as a function of I. I is just the number of the ants, so I is 1, 2, or 3, right? 1, 2, 3. And so what does that formula look like? Well, something like this. So if I is equal to 1, then the distance, as I is equal to 1, n is equal to 3. So if I is equal to 1, that means that the distance from the axis of rotation is L/3. So we would say this one is roughly L/3 from the axis of rotation, which, I guess that's where its head is, I guess, but close enough. And then if I equals 2, well, then that's L times 2/3. So this is ant number 2, so that's the distance to the axis of rotation here. Can I do this, right? Would be 2/3 times L, which makes some sense. And then if I equals 3, well, that's 3/3. The distance axis of rotation is just L. So this makes moderate amounts of sense, moderate to a lot of sense. And so we can stick this into here and see what we get. Okay, so I'm going to do that. So stick that into here. We get L squared. Now L squared is just whatever it is. It's the size of the object. So that can come out of the sum. Same thing with n squared. That can also come out because it doesn't depend on which ant we're talking about, where there's only 3 ants. Okay. And so we've taken this scary looking thing, converted into this converts into that. So the last thing here is this. So in the next slide, I think we're going to put this all together here. Now, right, so this is that. Now, let's just talk just about this term, the sum over I. So remember, we're just counting ants here. And so if there was more than 3 ants, it would be 1 squared plus 2 squared plus 3 squared plus how many ants that we have. Here it's just 1 squared plus 2 squared plus 3 squared because there's only 3. But let's say there's more than 3. We're breaking it up into many, many chunks. You can count this up and it actually gives you a number. This turns out, there's n is finite, so it's not necessarily going to give us infinity. So if you look up this formula on Wolfram Math World, the fancy name for this is the power sum. It will tell you that this is the equation for that. Personally, I could not derive this equation to save my life if I had to, but I'm very happy that Wolfram Math World can tell me what it is. And what's interesting is that we can test this out. So for example, so for n equals 3, right, you get 1 squared plus 2 squared plus 3 squared. So 1 plus 4 plus 9. So that's 5 plus 9, that's 14. All right, let's see if this works. So n equals 3. So that's 27 times 2. I can do this on my calculator, my phone here. So it's, let's see. Here we go. I know this is riveting television. So 27 times 2 is 54 plus 3 times n squared. So that's 3 times 3 times 3. So it's another 27, right? Plus n is 3. Plus 3, it's 84. Divide 84 by 6. Boom, 14. So you get the same thing as this. Okay? So this works. So that's good. It works at least for n equals 3. I think we can assume that it works in general. The thing to notice here is that, in reality, we're not going to be breaking these things up into just 3 pieces, right? We could break it up into a mole, right? 6 times 10 to the 23 pieces if we wanted to, if there's that many particles in it. So we're really going to be concerned about the large N behavior of this. The easiest way to think about that is that let's say that N is 10. So if N is 10, then this is 10. 10 squared, that's 100. 10 cubed, that's 1,000. So compared to 10, 300 and then 2,000. 2,000 is definitely the biggest number in there. And so we can approximate this as n cubed over 3. And in fact, that actually works moderately well even for n equals 3, right? So n cubed is 27, right? So 27 divided by 3, that gives us 9. Still in the ballpark of what we're supposed to get even for n equals 3, okay? So this is what you get for the large N behavior. And so now we can use this, put it all together, and figure out what this rotational inertia is. So here we go. Putting it all together, we get this, right? So if you take what's on the previous page, combine that all together. Remember, we had an m total over n, and we had an L squared over n squared, so that gives us an n cubed on the bottom. And then this thing gives us n cubed over 3. And so notice that the n cancels. And we just get 1/3 ml squared, which is what we expected to get, actually. So if you look in the table, indeed that is what it is. So this approach works. I don't necessarily need you guys to try it at home, but if you want to try to reproduce the other numbers on the table. But this is how you would do it, basically. And by the way, it's kind of nice that it does not depend on exactly how many chunks you break this thing up into. It would be rather weird to have a different answer for this if you break it up into 5 chunks, or if you break it up into 10 chunks, or 1,000 chunks, and if you get like different answers here. That's kind of strange. It would really make the most sense if this did not depend on your imagination of how many little tiny bits you're going to break this thing up into mathematically. So this is a good thing and almost kind of an expected thing. Anyway, so That about covers it. The next part I recorded earlier, and I'll let you watch that. Thanks. Okay, so I want to do another application of torque, and this is a situation that matters. So if you're sort of in the biology world or biomedical world, this is kind of interesting. But kneecaps, um, and if you're interested in the history of mob retaliatory practices, this is why kneecaps are so important. Um, so if you have a kneecap, if you're lucky enough to have a kneecap, then uh, here's kind of a demo here. We've got a hinge. We're pulling up with this rubber band, which is attached all the way at the bottom there. And if there's a kneecap there, then you get this nice movement. But if there's no kneecap, then even if you're pulling with the same force, it pretty much does nothing. I mean, almost nothing. It moves it just a little tiny bit. So in the context of what we've been talking about with net torque, how does this make sense? So if this is the schematic of the kneecap, there's some angle here, there's the kneecap there. How does the presence of the kneecap here help to increase the net torque? And this is the formula for the net torque from a lecture or two back. The net torque is the perpendicular force times the lever arm. So there's a lever arm here. And then that breaks down into the force times the angle there. So you'd like the angle to be 90 degrees if you can. But anyway, in this context, you've got a couple different options to think about. One is that this does not actually increase the net torque. Maybe I'm just trying to psych you out. Another option is that it increases, having the kneecap here, it increases the force somehow. Or having the kneecap here increases the distance to the lever arm. The fourth option is that it changes the sine term, and that's the secret sauce somehow. So think about it for a second. While I twiddle my fingers like a mad scientist that I am. You want to know? The answer is D. Okay. So here's the schematic here. So this is without a kneecap. So without a kneecap, then the rubber band is going to be at a very small angle to the bottom here. So in other words, the force from this rubber band is it's mostly pulling up. It's only a little bit pulling that way. And so this angle is going to be pretty small. And that's important because the perpendicular force is what actually moves this thing. And so, again, the rubber band is mostly up, not so much this way. And so we can calculate what the net torque would be. So here again is our force. Let's assume 400 newtons for the force. Assume that this distance is 0.2 meters.
Sine of 1 is a very small number, right? 1 is a small angle, but sine of 0 is 0, right? So sine of 1 is still pretty small. And so we can run the numbers there, and even though this force is 400 newtons, which is pretty big, because this is so small, we get 1.4 newton meters there. So overall pretty small. No, it's not going to move things too much. But if there's a kneecap there, then instead of having an angle of maybe a degree, maybe it's 10 degrees. And so you can stick this in your calculator and say, all right, well, if we pull with the same force, 400 newtons, but now sine is 10 degrees instead of 1 degree, then that significantly increases this. So instead of being 1.4 newton meters, now it's going to be like 14. So quite a lot more torque than it was before, and as you can see in the video, this does a pretty good job of lifting the knee. So, so the moral of the story is don't ever kneecap anyone. Don't deprive them of their kneecaps. Kneecaps are very important. You pretty much can't walk without them. Sorry if that got a little morbid there, but you know, it's this online delivery method, and so I've got to edutain, right? All right. So next thing to talk about is what's called the parallel axis theorem, and I will admit that there's not. I'm not sure that we're really going to test you on this in the midterms, but there are questions on the homework that are basically impossible to do without this, so listen up. And the basic idea of this is that, let's say that you want to rotate an object, but not around its center. And so when you look at that table of all the rotational inertias, and you say, well, there's a sphere there, and they give me the formula for the sphere, but what if I don't want to rotate it about the middle? What if I want to rotate it about over here and have the sphere go over this way or something like that? So in that situation, you want to do something like this. You want to take the rotational inertia about the center of mass, and then add to it the mass of that object times the distance to whatever actual movement that it's going to have. So it's going to be moving in some kind of a circle, right? And so whatever the distance is from the center of that object, the distance from the center of that object to where it's actually rotating, that's what this d needs to be. I'll give you some examples of that in just a second. And then if you add these two things together, that gives you the rotational inertia that you actually do need to use to either calculate rotational kinetic energy, or if you need to calculate, say, the angular acceleration based on some amount of torque. So the best example of this, I think, is this case. Sorry, I think I just said all these things. Best example is this case. Now, this is just lifted directly from that table in the book. And the thing that you may not have noticed before is that there's a little ICM here, or there is not an ICM here. So the CM stands for center of mass. And so the point of this is saying is that this object is rotating about the middle, right? And so this rotational inertia is the object rotating about its center of mass. But in this case, I mean, it's basically the same object, but it's not actually rotating through the middle. And so we cannot put the CM here. So it leaves that part off. And so the question at this point is can I use the parallel axis theorem to go from this to this? Can I use it for that? So let me show you how to do that. And so to do that, we are going to start with this, because you always want to start with the thing that is rotating around the center of mass. And if you didn't know what this rotational inertia for the thing rotating about the center of mass is, the parallel axis theorem is not actually going to be able to help you, by the way. So you're starting from this thing so that you know what this number is, right? If I gave you the length and the mass or whatever. And then we're going to shift the rotation by a distance d. So if you think about how far are we shifting the rotation here, going from this thing to this thing, Well, if you look carefully, it's, the total length of it is L, so that's not really changing, right? The main thing that is changing is that the axis of rotation is now sort of shifted by half of L, so L over 2. So I can stick that in here. By the way, the mass here is the same as this mass, so we don't need to worry about that. The mass is the mass, thankfully. So center of mass, so this is that. And now D, I just argued, it has to be L over 2, so I can stick that into there, L over 2. And so now it's just a little bit of, squaring fractions and things like that. So L over 2 squared is going to be L over 4, right? Or L squared over 4. So I can square this out. Right, so I get L squared over 4. Right, so this is the same as before. So 1/12 plus 1/4, we have to find the common denominator. So 1/4 has a common denominator of 12. So 3 on the top times 4 on the bottom. So that gives us 3/12. 3/12 plus 1/12 is 4/12. And then 12 is 4 times 3, so this gives us 1/3 ml squared. And we did it, right? Because that's exactly what we just got here, okay? So we use the parallax, and we use this crazy thing to figure out that if you want to know how much rotational inertia you would have if this thing was rotating off axis, not around its middle, then according to parallaxis theorem, it's 1/3 ml squared. That's basically where they got this number in the first place, by the way. So there you go. So it works. Now, what I do want to say is that it works in the forward direction, but it does not actually work in the backwards direction. So, for example, so you cannot start from this thing and go to that thing. Okay? So you cannot switch the script here and say, I want to figure out what ICM is, knowing only I. So that does not actually work. So just be careful about that. You have to start with something that's rotating about its center, and then displace that. Okay? Which I think is what this slide is basically saying. All right. Now the last thing is the worksheet. So I think this is an interesting example. So it turns out that when you are lifting, so we can think about this in terms of torque, right? So if I'm holding up a barbell, these people are much more strong than I am. If I'm holding up a barbell like this, my bicep muscle has to, exert tension on my forearm to prevent my forearm from falling this way, right? So schematically, it looks a little bit like this. So the figure credit here is Anatomy and Physiology According to Physicists by Professor Chris Orban at Ohio State Marion. And your bicep is kind of, it's attached close to your shoulder, and it goes down. It doesn't completely attach right at your elbow. There's some distance between where your bicep attaches and your elbow there. And so there's some tension. And we want to figure out how much tension force is that if you're holding a barbell of a particular weight. And I can't quite remember exactly what the weight of the barbell is in the worksheet, but you'll need to think about what's the angle here and exactly how much tension is this. And the answer will surprise you. It's a surprisingly large tension in your bicep. Your bicep has to supply in order to hold this thing up. So I hope that you're pleasantly surprised and at least quasi-entertained by doing this worksheet. So with that, I think that about sums it up. So there's the dimensions there. And so please go ahead and submit your, fill it out. Either you can print it out and work out on paper if instead you want to fill it out on your iPad with your Apple Pencil thing, that's fine too. But go ahead and fill that out and then submit that to the participation grade for today. So, and with that, signing off.